Okay, so now let's provide some theoretical underpinning to our discussion of common delta in the epsilon delta definition of continuity on an interval for a given function. So any function that exhibits such a common delta is called uniformly continuous. So let's give a definition. So definition, f is uniformly continuous on an interval I if for any epsilon greater than 0 there exists delta greater than 0 such that x1 minus x2 is less than delta, implies that f of x1 minus f of x2 is less than epsilon. All right, so for any 2 points, if the distance between them is less than delta, then the difference between the absolute values is going to be less than epsilon. And this, by the way, should be true for any x1, x2 inside the interval I. All right, so if we fix one of those points, let's say x1, then for every epsilon there exists a delta such that the epsilon delta definition of continuity is satisfied. So trivially, if f is uniformly continuous on I, then f is continuous on I. The reverse of this is, of course, not true, as we have seen from the examples below, above. So let's go back and see which functions in our examples were uniformly continuous, which ones were not. Let's see, the first example we considered was function x squared on the interval from -1 to 1. And in this case, we were able to determine a common delta. And so that function is uniformly continuous on the interval from -1 to 1. For the example number 2, on the interval from 0 to infinity, for the same function, x squared, we were not able to find the common delta. So that means that x squared on the interval from 0 to infinity is not uniformly continuous. So first, uniformly continuous, second, not uniformly continuous. The third example was 1 over x squared on the interval from 0 to 1. Again, in that case, we were not able to find the common delta, right? Because the function became eventually very steep as x is close to 0. So this function is not uniformly continuous either. Same is true about sine of 1 over x. We were not able to find a common delta in this case, so not uniformly continuous. And for square root of x on the interval from 0 to 1, we were able to find such a delta, a common delta. So square root of x is also uniformly continuous on the interval from 0 to 1. So in the examples above, f is uniformly continuous, and so that I don't write uniformly continuous 10,000 times in a row, we'll just call it UC. In examples 1 and 5. Note also that the function might be uniformly continuous on one interval and not uniformly continuous on another interval. X squared from -1 to 1 was continuous, uniformly continuous, and f from 1 to infinity was not uniformly continuous. Also, if a function is uniformly continuous on some interval, it must be uniformly continuous on a subinterval, right? Because if there is a common delta for the larger interval, there is a common delta for the smaller interval. All right, and at the end of the last class, we produced the following summary. We said that common delta seem to exist if f is continuous on I and I is a closed and bounded interval. So now we can rephrase this by just saying that function should be uniformly continuous, or seems to be uniformly continuous, if it is continuous on an interval I and I is closed and bounded. And so this allows us to formulate our first theorem about uniformly continuous functions. So theorem, f is, let's write it this way. Suppose that f is continuous on I, where I is a closed and bounded interval. Right, closed means that it includes m points as usual, and bounded, clear what it means, right? It's an interval which has a finite extent. So if this is true, then there should be a common delta. So then using our new definition, then f is uniformly continuous on I. All right, so drawback of formulating a theorem is that we now have to prove it. So let's do so. So proof. And we're going to use a contradiction here. So suppose that f is not uniformly continuous on I. What does it mean? It means that for a given epsilon, I cannot find a common delta. So there exists, what is the definition of uniform continuity? For every epsilon, there exists a delta such that something is true about 2 points inside the interval I. So the opposite statement to that, instead of any epsilon, so then we'll say then there exists an epsilon greater than 0, right? So if a statement doesn't hold, then at least for one epsilon, it's not going to be true. So that there exists an epsilon greater than 0, such that in a definition we say for all epsilon there exists a delta. So the opposite is that for this one selected epsilon, there are no deltas. So that means that for every delta, your original statement will fail. Okay, so there exists an epsilon such that for any delta greater than 0. Now, what does mean the statement will fail? It means that I can find 2 points on a distance less than delta from each other, such that on the other hand, f of x, so f of the first point minus f of the second point, should still be greater or equal than epsilon. So for any delta greater than 0, there exist 2 points, x1, let's call it x1 delta and x2 delta, inside the interval I, such that x1 delta minus x2 delta, the distance between those 2 points, is less than delta, but the difference between f of x1 delta and f of x2 delta, that difference is greater or equal than epsilon. Right, so that's what it means to have an opposite to the statement of our theory. Okay, so then if this is true for any delta, I'm going to consider delta equal to 1 over n, and this is for any natural number n, right? So then, because my original statement is true for all deltas, I'm just going to concentrate on deltas equal to 1 over n. So then, my statement will reduce to the following. So let me just copy this. Okay, so then there exists an epsilon such that for any n in n, right, I'm basically considering the same statement, but I don't need to consider all possible deltas. I'll just consider deltas that are equal to 1 over n. So there exist 2 guys, x1n and x2n, such that x1n minus x2n is less than delta, which is now 1 over n. But f of x1 n and x2n, that difference is greater or equal than epsilon. Okay, so what have we got then? So therefore, we now have 2 sequences. X1n, x1n and x2n. Both are contained inside I. Okay, but I is a closed and bounded interval. So I is bounded, and therefore both sequences x1n and x2n, those are bounded. Now, a priori, they're just 2 sequences inside the interval I. We now know they're bounded. But we don't know anything about them in a sense. We have no idea if the sequences converge or not, for instance. And typically we would want a sequence to converge because that will allow us to make some conclusions about a limit of that sequence. Well, but because both sequences are bounded, in fact, just because the first sequence is bounded, I can use Balzano-Weierstrass theorem. And Balzano-Weierstrass says that the sequence must contain a convergent subsequence, right? And so what I'm going to do is I'm going to select that convergent subsequence. So there exists a convergent subsequence our notation will become a little bit heavy, but there is not much we can do. X1 and K, right? So that the limit as K goes to infinity of X1 and K is equal to some number x0, right? Fine. Then we already worked with convergent sequences in inside closed intervals. And if a sequence converges inside a closed interval, then the limit must belong to that interval. Right? So if the sequence converges inside an interval, it either converges to a point inside the interval or to one of the endpoints. And if the interval is closed, then it must, in both cases, to converge to something that lives inside the interval. So because I is closed, x0 is inside I, right? Again, our subsequence is completely inside I, and it converges, so it must converge to a number in I, because I is a closed interval. All right, also. Now let's look at the corresponding subsequence of x2n, right? So also if we consider x2n k, right, a corresponding subsequence of x2n. So I'm selecting the terms with the same indices from a sequence x2n. Then we know that x1 and k minus x2 and k, that this is less. Let me see what I can do with this. This is less than 1 over nk, right? Because that's how we selected our x1, x2, right? They have to be on a distance less than 1 over n from each other. Well, and because n goes to infinity and k goes to infinity as k goes to infinity, right? Because if I choose a sequence n that goes to infinity, and out of that sequence I select a subsequence nk, then as k goes to infinity, then nk must go to infinity because if a sequence has a limit, then every subsequence will have exactly the same limit. Actually, let me change it like this. We have that the limit as k goes to infinity of x1 nk minus x2 nk, right? The difference is less than 1 over nk. Nk goes to infinity. That means that this limit must be equal to 0. And if the distance between x and k, x1 and k and x2 and k goes to 0, and the sequence x1 and k converges to x0, that means that the second sequence also should converge to x0. So we conclude that the limit as k goes to infinity of x2 and k, that it also must be x0. All right, so what are we going to do with this? So now we know something that we haven't used yet. So we also know that f is continuous on I. And therefore, by sequential definition of continuity, what can I conclude? x0 is a number in I. Limit of x1 and k is x0. So that means that by sequential definition of continuity, I have that the limit as k goes to infinity of f of x1 and k must be f of x0. And likewise, I know that x2 and k also converges to x0, and x2 and k is inside I, x0 is inside I. So again, the same sequential definition of continuity says that the limit as k goes to infinity of f x2 and k, this also is equal to f of x0. And then if I use properties of limits, then what can I say about the limit as k goes to infinity of f of x 1 and k minus f of x2 and k? Both are converging to the same limit. Limit of a difference is a difference of limits. So this is the limit k goes to infinity of f of x n and k1 minus the limit k goes to infinity f of x2 and k. This is f of x0 minus f of x0, so it's equal to 0. Right? Okay, and then if the limit of something is equal to 0, therefore, given any epsilon, there exists a k, right? There exists a k, let's say capital K, in R, such that k bigger capital K implies that absolute value of the term of my sequence minus the limit, which is 0, that is going to be less than epsilon. right? Well, we have been doing this now for quite some time, so let's remember what we actually said in the beginning. How did we select sequences, numbers x1 and an x2n? We selected them in such a way so that the difference is greater or equal than epsilon, right, for every n. And in particular, it should be greater or equal than epsilon for every nk, because I'm just looking at subsequence at some numbers, x1 and x2n. But for all of them, the absolute value of the difference is greater or equal than epsilon. And here we're having the conclusion, we got a conclusion that the same thing must be less than epsilon. And so that is a contradiction. And so therefore the theorem has been proved. All right, so that's it. So if the function is continuous on a closed and bounded interval, there is always a common delta in the definition, epsilon delta definition of continuity, or the function is uniformly continuous. Okay, so now we can use this theorem to prove that the function is uniformly continuous without actually playing with deltas and epsilons. So let's consider again example number 1. We had f of x equal to x squared, and I is an interval from -1 to 1. This is a continuous function. And this interval is certainly closed and bounded. Right? So therefore, by the theorem that we just proved, f is uniformly continuous on I, right? And we don't need to mess around with epsilon delta definition. Likewise, for example number 5, f of x was square root of x, and I was closed interval from 0 to 1. Well, certainly f of x is continuous on I, and I is definitely closed and bounded. Remember, it took us some time to figure out that there is a common delta in this case, but here we just apply the theorem, and again we see that f is uniformly continuous on I. Let's do one more example before we prove another theorem. Let's consider f of x equal to square root of x, and I, let's say, is an open interval from 0 to 1. Is my function uniformly continuous on this interval or not? I cannot apply the theorem directly, right, because interval is open. So theorem does not apply because So function is still continuous, but the interval is not closed, although it is bounded. So because I is not closed. Well, but on the other hand, it applies on a slightly larger interval, right? And as we just discussed, that means that f is uniformly continuous on a closed interval from 0 to 1. But if it is uniformly continuous on a larger interval, it certainly is uniformly continuous on a smaller interval. So therefore, f is UC on open 0, 1 because 0, 1 is contained inside closed 0, 1. Right? Okay. So now let's look back at yet one more example. Let's say f of x is 1 over x. X is between 0 and 1. Now let's say in this case the interval is half closed. Again, theorem does not apply because the interval is not closed. But do I have the same remedy as in the previous case or not? If I consider this function an interval from 1 over x, including 0, but I cannot do that because at 0, the value of the function f of x is not defined. So it seems that in this case, there is no function on a larger interval which is going to be uniformly continuous and which is going to contain f of x. So this argument that I just used in the previous example does not apply in this case. And we actually know that 1 over x is not uniformly continuous because we proved that there is no common delta in this case because the function becomes, a graph of the function becomes very steep. Otherwise, if I compare two examples, continuous function on an interval that is not closed, 1 over x is continuous at all points from 0 to 1, interval is not closed. So just by looking at a function on an interval, in this case, I will not be able to say if the function is uniformly continuous or not because the two things possess essentially exactly the same property. But the first function can be extended to a continuous function in a closed interval, and therefore it becomes uniformly continuous. And the second function cannot be extended to 0, to x equal to 0 in a continuous way, so then it is not uniformly continuous. And that would be the next theorem that I'm going to prove, but actually before I prove it, let's establish one additional result, which is going to be useful. So, in fact, let me do it in a separate lecture before it becomes too long.